Welcome to my next video lecture for Philosophy 4400. This lecture is going to be about David Bohm's interpretation of quantum mechanics. This is a picture of David Bohm. David Bohm was a 20th century physicist who came up with an interesting interpretation of quantum mechanics that avoids most of the more counterintuitive consequences of the orthodox version of quantum mechanics, and it retains a closer to classical picture of physics. This is a quotation from David Bohm. He says, "Ultimately, the entire universe, with all its particles, including those constituting human beings, their laboratories, observing instruments, etc., has to be understood as a single, undivided whole, in which analysis into separately and independently existent parts has no fundamental status." We're going to talk in a future slide about why he says that and how that's supported by his version of quantum mechanics. Here are some basic postulates of Bohm's theory. So first of all, you recall that there is a discussion, a famous discussion in physics about whether light consists of particles or waves. There's similar questions about electrons and other elementary particles. And in traditional quantum mechanics, there's this idea of wave-particle duality, which is a very difficult to understand idea, which sort of proposes that it's kind of a particle and a wave at the same time, and it will show particle characteristics in some contexts and wave characteristics in other contexts. David Bohm avoids the confusingness of this by postulating that there are two things. There are particles and there are waves. Now, what about the waves? So the waves always evolve in Bohm's theory in accordance with the Schrödinger equation. As you recall, this is completely deterministic, and I've written a version of the Schrödinger equation here. What about the particles? So in this theory, the particle always has a specific position. It's always fully determinate, but we human beings do not know the exact initial position of a particle. In fact, it's going to turn out that we're never able to know the exact position of a particle. And Bohm proposes that the probability of a particle being at any given location is proportional to the square of the amplitude of the wave function at that location. This equation here that says rho equals psi squared. The thing on the left-hand side is the Greek letter rho, which is standardly used to represent probability density. This psi here, this is the wave function. So if you have a higher amplitude of your wave function, then you're more likely to find the particle in that region. Now, the role of the wave is basically to push the particles around. So the evolution of the wave function causes the particle to move in specific ways. It moves in the direction of the gradient of the wave function. In other words, basically, if the wave function is increasing in a certain direction, then the particle will move in that direction. And this is the equation that describes the way that the particle will move. Now, all of that was kind of assuming that you have a single particle, which is being pushed around by a single wave. But what if you have a system consisting of many particles? And in Bohm's understanding, there's a single wave for the multi-particle system. In fact, there might be a single wave for the entire universe. And this wave occupies a many-dimensional configuration space. This, by the way, is going to explain the quotation that we had on the first slide at the beginning of this discussion, where David Bohm was saying that the whole universe is an undivided whole. Okay, configuration space, what is this? It's a kind of mathematical space that a physical system occupies where there are three dimensions for each particle. The three dimensions for each particle correspond to the location in ordinary physical space of the particle. So for example, if you have two particles and the first particle is located at spatial coordinates 1, 3, -4, that's coordinates in ordinary three-dimensional physical space. And suppose the other particle is located at coordinates -1, 2, and 0. Then the two-particle system is located at the point 1, 3, -4, -1, 2, 0 in a six-dimensional configuration space. The configuration space, just by stipulation, it's got one dimension for the x coordinate of each particle, one dimension for the y-coordinate of each particle and one dimension for the z-coordinate of each particle. Right? And so you can represent the system as a whole as being at a single point in that configuration space. Now note that, of course, the configuration space is going to have a ridiculously large number of dimensions if you have a macroscopic system. So the universe as a whole occupies a single point in a configuration space that has it's got 3n dimensions, where n is the number of particles in the universe. Okay, these are interesting features of David Bohm's theory. So the postulates C and D imply that the probability distribution for particle positions at any later time will also be proportional to the square of the amplitude of the wave function. So that is, if you start out with a probability distribution that's proportional to psi squared, and if the particle always moves in the way described by Bohm's equation of motion, then the probability distribution for the possible locations of the particle always continues to be proportional to psi squared. And by the way, the reason for that is that the equation of motion was specifically designed to have that effect. What Bohm basically did was figure out what the equation of motion had to be in order to preserve this. Another interesting feature is that the theory is deterministic. So you might have heard that in quantum mechanics, nature is governed by chance, and that is true in the orthodox interpretation of quantum mechanics, but it doesn't have to be true. So in David Bohm's theory, it's deterministic, although you could create an indeterministic version of it. David Bohm discusses this in his book, The Undivided Universe, where he suggests that if you wanted to have indeterminism, you can incorporate that into his theory, but you just don't have to. Note that Bohm's theory gives the same empirical predictions as standard versions of quantum mechanics. It uses the same mathematics. It uses the same predictions for the probabilities of measurement results. You get that from having this postulate where the epistemic probability of finding a particle in a location is proportional to psi squared. Now, there is one exception to this. There is an in-principle way of empirically distinguishing theories like David Bohm's from theories that have a wave function collapse. If somebody can give a sufficiently precise theory of the wave function collapse, then it is in principle possible to test for whether wave function collapses occur. Basically, because if you have a wave function collapse, then that prevents interference effects. So however, it's extremely difficult to actually test for wave function collapses because the wave function collapse is supposed to occur when you get a macroscopic effect, according to the Copenhagen interpretation. And it's very difficult to try to produce an interference effect for macroscopic objects, basically because you have to account for every particle in the system. You have to arrange things just right. Okay, so it's unlikely that we would actually be able to test for this, but Bohm's theory predicts that there's no wave function collapse. The wave function always evolves according to Schrödinger evolution, and that's in disagreement with the Copenhagen interpretation, which says that you get a collapse when an observer measures something. Also interesting is David Bohm's theory is non-local. Now, we discussed in the video lecture about non-locality in Bell's theorem the fact that quantum mechanics in general is non-local. David Bohm's theory has very explicit non-locality. He has everything in the universe being interconnected because everything is represented as the position of a single particle, the world particle, if you like, in this many-dimensional space. So instantaneous action at a distance in physical space is possible. There's no action at a distance in configuration space, but in physical space, yes. Also, his theory implies that properties other than position are contextual. And what I mean by being contextual is the value of the property depends upon the relationship of the measured object to its environment. So if you use different ways of trying to measure the property, you can get different outcomes. So for example, the spin of an electron in Bohm's theory is not an intrinsic property of the electron. If you try to measure the spin in different ways, you can get different measurement results. So if you change the orientation of the measuring device, you can get different results. Okay, but the position of a particle is an objective fact that doesn't depend upon your method of measurement. Okay, how does this theory explain the surprising and seemingly paradoxical quantum mechanical phenomena that we discussed in previous lectures? So consider the double slit experiment again. This is where you have this light source and it's sending light towards this wall that has two slits in it. The light can go through either slit. And then we notice that you get this kind of interference pattern on the wall where there are bright spots and dark spots in between them. Bright spots here and dark spots here. Okay, so according to Bohm's theory, you have the wave, the so-called pilot wave, which spreads out and it hits the wall and it goes through both slits. So some of the wave goes through here and some of it goes through here. And the parts of the wave that are coming through the different slits can interfere with each other. The particle, which is located at a specific place in the wave, it gets carried along with the wave. And it's unpredictable to us. It's completely deterministic in nature, but it's unpredictable to us just because we don't know the exact initial position of the particle. But the particle is going to go through one slit or the other. But what happens is, as the wave develops over space and it moves towards the wall, the particle gets carried along with the amplitude of the wave function. So in the places where the wave has a lower amplitude, it just pushes the particle away from those places. It's less likely to wind up in these places, and it's more likely to wind up here because the particle kind of moves along with the direction that the wave function is flowing. Okay, so that explains why you're going to see an interference pattern even if you're only sending one particle through at a time. Okay, and it also explains why the interference pattern is only going to occur if both slits are open. Because if both slits are open, then parts of the wave can go through both slits. If only one slit is open, then there's no interference because the wave can only go through the open slit, and then the particle can only go through that slit as well. What about explaining what happens when you make a spin measurement? So let's say that you have an electron which has y spin up for its wave function, and you feed it into this box for measuring x spin. What happens? What happens is the wave that the particle is in splits in two. It splits into an x spin up component and an x spin down component, and the two parts of the wave go through the two apertures of the box, indicating whether the particle would be x spin up or x spin down. Now the particle is located in a particular part of the region where the wave function is non-zero. And that is unknown to us, so there's a 50% chance that it's located in the upper part and a 50% chance that it's located in the lower part of the wave. If it happens to be located in the upper part, then what happens is it just gets carried along with the part of the wave function that goes up in the x-spin box. If it's happened to start out in the lower portion of the wave, then it will get carried along with the part of the wave that splits off and goes down. Okay, so that's how you get the results of the spin measurement. It's important to note that there's no wave function collapse in this theory. What happens is, so the two portions of the wave that split off, both of them still exist. The x spin down component of the wave function still exists. It just goes out here, and it's just not affecting what we observe because the particle isn't located within that part of the wave function. What we observe is going to be determined by the wave function, a part of the wave that the particle is located in. But there wasn't a collapse of the wave function. There wasn't a violation of Schrodinger evolution. Now, why will the electron subsequently be measured as an x-spin up electron with 100% probability? The reason is just that the x-spin down portion of the wave is going to be somewhere else. So this particle moves up along with this part of the wave function, and then if you feed it into another x-spin measuring device, the particle is then associated with an x-spin up part of the wave function, which forces it to wind up being measured x-spin up. However, because the x down portion of the wave function still exists, it is in principle possible for it to get directed back to the same location in space that the x up portion of the wave function is located at. And if that happens, it will turn back into a y-spin up electron. Now, how do we explain the mysterious two-path experiment that we described in previous lectures? So as you recall, perhaps, hopefully you recall, what we have is this apparatus where there's an X-spin box at the bottom. We imagine that you feed electrons into this apparatus that initially start out with Y-spin up. So let's say we've verified their Y-spin by measuring it, and they're all Y-spin up, and then you feed them into this X-spin box. If they come out x-spin up, they should go along the upper path and wind up at point E. If they come out x-spin down, they should go on the lower path and still wind up at point E up here, and then they get fed into a y-spin box. And the mystery is that we observe them to be y-spin up 100% of the time, even though they had their x-spin measured, which normally we think disrupts their y-spin and makes it random. So here's what happens. The electron is initially located somewhere in the part of the wave, in this y-spin up wave here. This goes into the x-spin box as described on the previous slide. The wave then splits in two. It splits into an x-spin up component that goes along the upper path and an x-spin down component that goes along the lower path. The particle is only on one of these paths, but the wave splits in two and takes both paths. Okay, so which path the particle takes, again, is determined by its exact initial location within the wave to begin with. Okay, then when the two parts of the wave function both wind up back at E, then they recombine and turn into a y-spin up wave function. And so that explains why if you then feed this into a y-spin box, it's going to come out as y-spin up. Okay, what are the advantages of David Bohm's interpretation of quantum mechanics? There are four important advantages. First, you get a uniform dynamics. What I mean by this is there's only one principle that describes how the wave function evolves. It always evolves in the same way. And you don't have to have different principles for measuring devices or observers from the principles that govern everything else in physical reality. The second important advantage is, you might say, logical coherence. So you don't have to have this notion of a superposition, which seems like it might be kind of a logical contradiction. If you have a cat in a box, it's always either alive or dead, referring to Schrodinger's cat. You never have a cat that's, somehow simultaneously alive and dead, or half alive and half dead, or anything like that. Also, the theory is, in a certain sense, more precise. That is, you don't have to rely upon a vague concept of measurement in order to explain what's going on, and you don't have to make a vague distinction between macroscopic and microscopic objects. Finally, the theory is compatible with determinism, if you consider that an advantage. Of course, that is philosophically controversial, whether that's really an advantage or not, but some people would consider that an advantage of the theory. What are the possible objections to this theory? So some people object to Bohm's theory because it blatantly conflicts with special relativity. It's a blatantly, explicitly non-local physical theory. So if you think about the EPR experiment, the outcome of the experiment, whether you get both electrons, whether you get, the electrons being spin up and spin down, or spin down and spin up, the outcome can depend upon the time order in which the two electrons get measured. And remember, these electrons can be outside of each other's light cones, so they can be at space-like separation. According to the theory of relativity, there's no objective time order to space-like separated events, but in Bohm's theory, what actually happens depends upon, so if you start from a particular specification of the initial conditions, and again, by the way, you don't actually know what the initial conditions are, but if you hypothesize a particular set of initial conditions, then you predict that what should happen after that point depends upon the time order in which the two electrons get their spin measured. Okay. Right, now that means that David Bohm's theory requires there to be a preferred reference frame. You have to have a preferred reference frame because that would specify the objective time order of different events. Now note that even though the theory requires there to be a preferred reference frame, we don't have any experimental way of identifying what the preferred reference frame is. So if you have scientists who are doing these spin measurements at these distant locations, there's nothing that the scientists can do to figure out which one of them made the measurement first. Okay, but there has to be an answer to which one of them made the measurement first, because the theory predicts that whoever made the measurement first, if the other person had made the measurement first, then there could have been a different outcome of the experiment. You also can't use this non-locality to send signals from one location to a distant location outside your light cone. And basically the reason for this is if you do a measurement on your electron, the person at the remote location can't tell that you've done it. They can't tell whether you did the measurement before they do it because they don't know what the outcome of their measurement would have been if you hadn't done yours. And the probabilities for the different possible measurement outcomes, if you've done your measurement first, are the same as the probabilities if you do your measurement after they do, right? And so they can't figure out whether you've done your measurement first or not. Another kind of objection that people might raise is a logical positivist inspired objection. So Bohm's theory entails that you can have undetectable facts, as just noted, especially the undetectable facts about the objective time order of certain events that are space-like separated, and more generally, undetectable facts about what the preferred reference frame is. Logical positivists object to this because they think if there's no way of verifying something, then the statement is meaningless. Okay, a third type of objection is David Bohm's theory doesn't make novel predictions. So the Copenhagen interpretation comes before Bohm's theory, and many people believe that you can't overturn an existing scientific theory unless you provide a new theory that is shown to be better, and the new theory, in order to be better, has to make new predictions that the old theory can't make. Bohm's theory doesn't make new predictions, at least not ones that we're practically able to test. Okay, and a fourth objection, you might think there's a kind of conspiracy of silence. This is kind of analogous to the objection to the Lorentz ether theory that we talked about in a previous class. It's kind of bizarre how the world apparently conspires to prevent us from detecting the preferred reference frame, or verifying the truth of determinism, or verifying the lack of wave function collapses. In other words, things are set up to make it look as if the orthodox Copenhagen interpretation of quantum mechanics is true, even though the theory, Bohm's theory, implies that it's not, and that we have something that's much closer to the classical picture of physics. A fifth objection is that the probabilistic postulate, rho equals psi squared, so the probability density for possible locations of a particle should be proportional to the square of the amplitude of the wave function. You might think that that's ad hoc. And so there isn't any underlying explanation for why that should be the correct epistemic probability distribution. Finally, a technical objection, it's difficult to come up with a Bohmian version of relativistic quantum field theory. In other words, the theory has been worked out for the non-relativistic case. They have not worked out a version of the theory that incorporates relativity and combines that with their version of quantum mechanics. Okay, so in conclusion, Bohm's theory avoids all of the amazing and counterintuitive things that are said to be shown by quantum mechanics. So in the popular literature, you sometimes hear quantum mechanics shows that observers create reality, that reality is dependent on us, the observer, or you hear quantum mechanics shows that reality can be indeterminate, or that there can be contradictory aspects of reality, that you could have the cat that's both alive and dead. Also, less counterintuitive, but possibly surprising to earlier physicists, is you hear that quantum mechanics shows that the world is governed by chance. Bohm's theory shows that we're not forced to accept any of those amazing consequences, you can have a picture that's much closer to the classical picture of physics. And in my judgment, the advantages of Bohm's theory are much more important than the disadvantages.